Okay guys, in this video we are going to start the next focus, which is going to deal with the first law of thermodynamics. And this first topic, which we're going to break up into two videos, deals with the subject of internal energy. Before we get into that, I wanted to talk first about an important concept in thermodynamics. The idea of a state function and the idea of a path function. So state functions are properties of a thermodynamic system, and they depend only upon the current state. And so these are things like the pressure, volume, number of moles, and temperature. In this topic, we're going to learn about another state function called the internal energy. And later on in the course, we'll discuss entropy and free energy in more detail. These are all properties of the system, and the value of these properties depends upon the current state and only on the current state. It doesn't matter how the system got into that state. State functions mathematically, when you are discussing an infinitesimal change in the state function, mathematically, you represent it by what's called an exact differential. And then in my notes, I'm using the lowercase d to represent the exact differential of a quantity x in this case. So dx represents an exact differential. And how you can use exact differentials, let's suppose that you wanted to calculate the change in a state function between some initial state and some final state. What you can do, conceptually at least, is to take an infinitesimal change in that state function and then add up all of the changes, all of the infinitesimal changes between the initial state and the final state. And for exact differentials, what you'll get is that the change in that state function is just the difference between the final value of the state function and the initial value of the state function. So this is a mathematical property of quantities that are called state functions. Another aspect of state functions, for extensive state functions at least, is that the change in the total system, or the change in that state function for the universe, can be broken up as a sum of the change in the state function for the system plus the change in the state function for the surroundings. So just to remind you where I'm coming from here, I'm talking about this kind of diagram like this, where you've got your thermodynamic system of interest and you've got its surroundings. You can think of properties of the system. The surroundings also has properties. And then you can think about that property for the entire total system. Okay, and so what this equation here is stating is that if you have a temperature change in both the system and surrounding, or not temperature, I should say, volume change, something that's extensive, the volume change for both the system and surroundings would be a sum of the volume change for the system plus the volume change for the surroundings. And take a look here at the notation. Whenever you don't include a label, notice I've included surroundings here and I've included total here. When you don't include a label, that implies that you're talking about the system. Okay, so just for future reference there. Another quantity in thermodynamics is called a path function. Okay? And so path functions are different from state functions in the sense that they are not properties of the system. Rather, they are properties of some path or some process that involves a change of state. Okay? And the value of a path function depends upon what path you take between the initial state and the final state. Not all paths are identical as far as path functions are concerned. There are two path functions that we'll talk about in this course. There's only two to worry about ever. Work is one, and the other is heat. Mathematically speaking, an infinitesimal amount of heat or an infinitesimal amount of work is not represented by an exact differential. It's represented by what we call an inexact differential. And here in my notation, I'm using lowercase d with a little bar through the top of it. Okay, so this notation here corresponds to an inexact differential. Other authors use different symbols. Sometimes a lowercase delta is used. Other times the author will just use an ordinary d. But for my notes, I'll be using this d bar symbol. You can calculate the finite amount of work and the finite amount of heat by doing an integral over an infinitesimal amount of work or an infinitesimal amount of heat. However, the value of the integral depends upon what path you take between the initial state and the final state. It's not calculated as simply a difference, like it is, for example, here for the case of an exact differential. Right? The value of this line integral or path integral, as it's called, depends upon what path you take. And so that's the major distinction between state functions and path functions. Properties of the system are state functions. Work and heat are not properties of the system. They are path functions. Over the course of the next couple of chapters, we are going to be calculating heat and work and some other quantities as well. And we need to pay attention in our problem solving. We need to pay attention to different adjectives that classify what type of path we're dealing with in a given problem. And we've already seen a few of these terms already. The term isothermal refers to a path where the temperature is constant. Isobaric means that the pressure is constant. And isochoric means that the volume is constant. We are also going to learn about the distinction between a reversible process and an irreversible process. Another adjective that's also used in typical physical chemistry work problems, the term free, in reference to a free gas expansion. So there's another adjective that we want to pay attention to. And another one is the term adiabatic, which means that the heat is zero for an adiabatic process. So these are adjectives that we want to get to know. We want to know what they mean, both in words and also in terms of how to use these adjectives to help us solve problems. So what are the mathematical implications of these different terms? The purpose of this slide is to essentially define three types of thermodynamic systems: open systems, closed systems, and isolated systems. So these adjectives, they refer to the boundary that separates the system and surroundings. The boundary is very important because it controls how energy and matter can be exchanged between the system and surroundings. And so this diagram here depicts what these different categories are. For an open system, the open system can exchange both matter and energy with its surroundings. The closed system can exchange only energy, and the isolated system can exchange neither energy nor matter. Okay, and so that's an effect of the boundary. We have different adjectives that are used to classify the boundary on this slide as well. So a diathermal wall separating your system and surroundings is one that does conduct heat. Contrast that with an adiabatic wall which does not allow heat to flow. So an adiabatic wall would be an insulating wall. The term movable and non-movable, or flexible and rigid, these are different types of walls that are important for the flow of energy associated with doing work. For example, when you have a movable wall, that means that your system can do work on your surroundings, or your surroundings can do work on the system. But if the walls of the container are rigid, then you cannot do any work. With respect to the exchange of matter between the system and surroundings, you would talk about permeable walls or non-permeable walls. In some cases, for example, when we talk about osmosis, we'll talk about semi-permeable walls. Permeable walls allow matter to flow between the system and surroundings. Non-permeable does not allow matter to flow. And then a semi-permeable wall is one that allows certain types of matter to flow between the system and surroundings, but not other types. Here we're basically defining what heat and work are. Recall these are path functions, and they are associated with energy that is exchanged between the system and surroundings. Okay, so there's two ways to exchange energy between a system and surroundings. One of them is work, and the other one is heat. So starting with heat, it's an amount of energy exchanged. So it's measured in joules or kilojoules. And it's energy that is exchanged because there is a temperature difference between the system and the surroundings. So whenever your system and surroundings are at different temperatures and you have diathermal walls, you're going to have energy flow between the system and surroundings via heat. The terms endothermic and exothermic, they refer to the system. So endothermic means that the system absorbs thermal energy via heat from its surroundings. Exothermic means that the system releases thermal energy via heat into its surroundings. So you've heard these terms before. Make sure that you know what they mean. We're going to use them a lot, in particular when we start doing the thermochemistry calculations. Work is also a quantity of energy that is exchanged between the system and surroundings. However, it's due to a difference in force. So whenever you have a movable wall and the pressure on the system side of the wall is different than the pressure on the surrounding side of the wall, then that wall is going to move until the two pressures come into equilibrium with one another. And so this is where work comes from, because you've moved a wall in the system or the surroundings. The terms endergonic and exergonic can be used to describe work from the system's perspective. So an endergonic process is one where work has been done on the system. An exergonic process is one where the system does work on the surroundings. And note what it says on the end. So this is true for both the endothermic process and the endergonic process. The system's energy increases. For the exothermic and the exergonic process, that causes the system's energy to decrease. Okay, so we kind of take a system-centric view in using these terms. Notice the effect of the boundary in this figure. So here we've got an adiabatic wall. Okay, so that's what this gray bar represents. And we're considering an endothermic process. So in an endothermic process where no heat can flow, you're going to see that the temperature of that system decreases. Contrast that with an exothermic process for adiabatic walls. You're going to find that the temperature inside the system is going to go up. If you remove the adiabatic wall and replace it with a diathermal wall that allows heat to flow, when you have the endothermic process, the system will absorb thermal energy from the surroundings via heat, and that can keep the temperature steady, right? The temperature will stay constant, typically with whatever the temperature of the surroundings is. Contrast that with an exothermic process and diathermal walls. What you'll find is that energy will leave the system via heat, but the temperature won't change. This is kind of an interesting take that Atkins has on describing heat and work at the molecular level. He characterizes heat as a process that involves random molecular motion in the surroundings. So here's a diagram he uses to explain that. So it really doesn't matter at the molecular level what's happening in the system. You know, if you want to distinguish between heat and work, here we've got a process where energy is leaving the system. And what does that energy do in the surroundings in the case of heat? It increases, the vigorousness of that random motion of the molecules in the surroundings. Okay, so the molecules start moving faster, but they're moving in a random way. So this is what we call thermal energy. Okay, so that's heat. Contrast that with work, which involves organized molecular motion in the surroundings. So when you do work, the system is pushing or pulling on the surroundings, and that causes all of the molecules in the surroundings to move in a unified way, in a concerted motion, like the system is pushing the surroundings away from itself. Okay, and so this organized motion is what we call work, whereas this randomized motion, change in motion, I should say, is what we call heat. This slide introduces us to the idea of the internal energy of a system. So this is a property of the system. Okay? Work and heat are not properties of the system or the surroundings. They're properties of a process. However, the internal energy is a property of the system. So it's an extensive property. That means that if your system gets bigger, that is, if you double the size of the system, it's going to have double the energy that you had before. Internal energy is also a state function. Okay? And its sort of physics definition is that it measures the system's capacity to perform work. And then I like to tack onto that, you could also do heat with the system's energy. How to think about internal energy from the microscopic point of view? Well, I'd like to refer you back to that one-to-many picture that we looked at in the, I believe it was the prologue lecture, where you need only 4 variables to describe a thermodynamic state, but that single thermodynamic state corresponds to a whole bunch of possible molecular, total molecular states. You can think of the internal energy as the time average of the total molecular energy state. And I have a figure here illustrating what I mean by that. For a given thermodynamic state, microscopically, the molecules are bouncing all around, and they're bouncing back and forth between different total molecular states. Just through collisions and just due to the fact that everything's moving around and interacting with the surroundings. So the total energy of the molecular state is bouncing all around, okay, with time. And what you can think of the internal energy, you can think of the internal energy as the time average of that molecular energy state. Okay, so the molecular energy state is bouncing around some average, and then that average corresponds to what we call the internal energy of the system. And so here it's expressed as an average. If you were to try to calculate it, you would need to know what the molecular energy is as a function of time, and then you would integrate it over some time interval and then divide by the time interval, and that would give you the internal energy. What contributes to that total molecular energy? Well, you've got n molecules. Okay, so we're going to assume that they're independent of each other, more or less. And they have kinetic energy, right? So there's a kinetic energy contribution to the total molecular energy. There's different ways that you could properly express the potential energy, but we're just going to make it simple and say, okay, every molecule has some potential energy due to its interactions with its neighbors. This isn't a very precise formula, but there's some potential energy corresponding to every molecule. And then the molecule may have some internal energy components to it. You know, for example, a molecule might be vibrating or rotating. It might have some electronic energy, things like that. Things that are separate from kinetic energy and potential energy. So you would add that up for every molecule, right? N would be on the order of Avogadro's number for a real macroscopic system. And because the molecules are moving and interacting with one another, and this energy is time dependent, essentially, just because there's interactions with the surroundings. So what I am showing you here is something that we've seen in the previous video when we talked about real gases. So here we're looking at the potential energy of, say, a molecule interacting with another molecule as a function of the distance between the molecules. When the molecules are far apart, they do not interact strongly at all, so the potential energy goes to 0. When the molecules are spread away from one another, so like in a gas, in an ideal gas, the molecules don't interact with each other very much. In this intermediate region, we have attractive interactions, and then at very close range, we have these repulsive interactions that tend to push the molecules apart. This region out here, where the molecules are far away from one another, we call that we say that the particles are essentially free of each other, right? So there's no interactions between them. We say that when there's no potential energy of interaction, we say that the molecules are free. Let's see. So this is what I'm leading up to with this conceptual question here. I'm asking, how do attractive and repulsive interactions affect the internal energy? So what I'm essentially asking is as a function of the molar volume. So what I want us to do is think about, how does this diagram and the different regions relate to the internal energy as a function of the molar volume. So what we're really talking about is, how does this term affect things? And so let's go back to that figure and say, okay, when the particles have a very large molar volume, okay, that means that the molecules are not close to one another. And so there's essentially no interaction here. So that tells us that the potential energy is 0 when the molar volume is large. Okay, so going to the equation, if the molar volume is large, then the potential energy is 0. Okay, so that's going to have no effect on the internal energy. There won't be any contribution from potential energy when the particles are free. However, if you decrease the molar volume, that's going to bring the molecules closer together. And what that's going to do is that's going to decrease the potential energy. You notice it's going to be negative, right? So here, as you start squeezing the molecules together, this number is going to become negative, right? And that's going to end up decreasing the internal energy. So when you have strong attractive interactions in your system, that's going to cause the internal energy of that system to decrease. what about if you really try to push the molecules together and you enter this repulsive domain? So now we're talking about small molar volumes. The molecules are really close to one another, so the interactions, the repulsive interactions, are kicking in. That's going to make the potential energy more positive, and that's going to end up increasing the internal energy. So the take-home lesson here is that attractive interactions decrease the internal energy. Repulsive interactions increase the internal energy. And when the molar volume is large, the molecules don't feel one another. There's no effect of the potential energy on the internal energy. We can go ahead and skip the P and Z. We've essentially already done that analysis when we looked at the compressibility factor. So, well, let me think about that. Essentially what I wanted to point out is that, if you, I'll just refer you back to that video where we discussed real gases and pressure and the compressibility factor. Now you have a way of correlating that with the internal energy. So I'll just leave it at that, I think. Let's talk about this next subtopic. We have discussed the kinetic molecular theory in a previous video as well. And here I wanted to make a connection between that discussion and the internal energy. So in kinetic molecular theory, you can actually calculate the internal energy of an ideal gas for the case where the gas is non-interacting, which means the molecules have no potential energy of interaction between them, and structureless means that there's no internal state energy. Okay, so going back to this previous equation, a non-interacting gas means that this term is zero, and then if it's a structureless, if the molecules are structureless, what you're basically saying is that the internal state energy is also zero. So basically the kinetic model includes only kinetic energy as the contribution to the total molecular energy. Okay, so for that case, you can actually pretty easily calculate the internal energy of the system. Okay, so conceptually, what you would do is you would take the average kinetic energy of every molecule and then add them together. And the kinetic energy of a given molecule can be broken down into the x component of its kinetic energy, the y component, the z component, and then if there's additional kinetic energy associated with molecular rotations, you can add those in as well, okay, and they'll have a similar form. And what we can do is make use of a theorem from statistical thermodynamics called the Equipartition Theorem, which tells us that at thermal equilibrium, the average contribution for every kinetic energy component is the same and has the value of kT over 2. So this is a result from statistical thermodynamics. It tells us that every type of kinetic energy makes the same contribution to the average, to the internal energy. That's what I'm saying. And so the kinetic energy along the molecule's X component is the same as the contribution on average from the molecule's Y component of velocity and its Z component. And we also get the same thing for any rotations that we have for these molecules. So each type of kinetic energy contributes kT over 2. Okay, and so you would then replace each of these terms, this term and that term and the next term and the next one, you would replace that with kT over 2. And then you would add up over all molecules. And the result that you get is right here. Okay, so this is going to be a formula that you want to keep in mind. Okay, that this is the formula for calculating the internal energy of an ideal gas. The factor D refers to the number of kinetic degrees of freedom in the molecule. So let's suppose that you had a monoatomic gas. Well, monoatomic gases don't rotate, they can only move around in space, so they only have translational degrees of freedom. So the molecules can move in X, they can move in Y, and they can move in Z. Therefore, there's 3 contributions to the internal energy. So for a monoatomic ideal gas, the value of D is 3. So U would be 3/2 NKT, where N is the total number of molecules. If you like, you can convert that to moles using the molar gas constant. For molecules that have some structure to them and can rotate, linear molecules, they can translate in X, Y, and Z, so there's 3 translational degrees of freedom for kinetic energy, but then they can also rotate in 2 additional degrees of freedom. So let me quickly illustrate those with the camera. So a diatomic molecule or a linear molecule can rotate like this, and it can tumble out at you. So those would be unique rotations. However, this spinning motion here, the third axis, that doesn't contribute at all. Okay, so there's really only 2 rotations for 2 types of rotations for a linear molecule. That gives you a total of 5 kinetic degrees of freedom. So the value of D for a linear molecule would be 5/2 nRT. For a nonlinear molecule, okay, you can rotate in 3 different ways. And so you wind up with a total of 6 kinetic degrees of freedom. So you'd plug 6 in here for a nonlinear molecule, which would give you 3 nRT. Okay, so this is the formula, this is the kinetic molecular theory formula for the internal energy of an ideal gas. And we're going to get a lot of mileage out of this equation. Okay, so this is something that you should focus on learning, so spend some extra time kind of committing this to memory. And then what we're being asked to do here is to calculate the internal energy for an ideal monoatomic gas, and then repeat the calculation for diatomic and polyatomic gases. So for the monoatomic case, you're going to have that U equals 3/2. Let's see. We'll just do this for 1 mole of gas, nRT. For the diatomic, U is going to be equal to 5/2 RT. And then for the polyatomic, U is going to be equal to 3 RT. Okay, and so the calculations are very easy, so I don't think I'm going to even plug them in. You would just plug in 1 mole, the gas constant. You would want to use 8.314 joules per mole Kelvin. And then you'd plug in the temperature in units of Kelvin, so you'd use T equals 298. So it's a simple calculation, so I'll just leave the numbers to you just to get some practice with these formulas. But anyway, that's what we have here. And I'm going to go ahead and stop this video here, and we'll pick up with the first law of thermodynamics in the next one.